So we're going to continue on here for some special relativity stuff. The last video we did time dilation, where we figured out that time slowed down for people that moved really fast near the speed of light. And in this video what we're going to do is length contraction. What we're going to find is that the Lorentz equations, the Lorentz transformations, predict that when something is moving really fast, its length will be contracted. And so what I mean by that is if, for example, we had a meter stick here, and in its own reference frame, when you're looking at it and it's not moving relative to you, it has a certain length to it. But if it begins moving relative to you, depending on how fast it's going, this 1 meter will get squished and it will appear to be shorter than the regular meter stick. So if you had a meter stick and you had somebody else take a meter stick and go flying past you real fast and you held them up right as they passed, they wouldn't be the same length anymore. Okay, so let's take a look at this and let's look at, let's say this is our coordinates, because we can measure the length of something by looking at its first coordinate and the coordinate of its beginning and the coordinate of its end. That's velocity. So let's call this end of the coordinate of the moving one x2 prime, and we'll call this one x1 prime. Okay? And so if we look at that, we've got the length of the stick is simply the distance or the displacement between the end of the stick and the front of the stick, right? So that would be x2 prime minus x1 prime. And then if we were looking for that, we would say, all right, well, x2 from our Lorentz equations is gamma x2 minus vt, and then x1 prime is gamma x1 minus vt, and we can distribute the gamma x2 minus gamma vt minus gamma x1. Now minus a negative is plus gamma vt, and then we have gamma vt negative and a gamma vt positive. I'm not sure why I put the closing parentheses on there. Wasn't using anymore, but anyway, those cancel and you're left with just gamma x2 minus gamma x1, which is just gamma, that's a gamma, times x2 minus x1, and x2 minus x1 would be gamma delta x, where x2, x1, right, the coordinates of it, what its length would be in the stationary versus this. So this is very similar to our time dilation equation, very similar in form. And we can define a couple things. So one, like with time, we had proper time and dilated time. Well, we can have a proper length. This is the length, obviously, like how proper time was the time in the at-rest frame or in the observer's frame. This is the length in the at-rest or observer's frame. So if you have the length of this object while you are moving with it, while it's moving with you, while you are stationary relative to each other, that would be the proper length. If you then took it and started it moving relative to you, so you had your buddy grab it and go grab that same meter stick after you measured its length and or whatever object it is, and you had him take it and then run past you really fast near the speed of light, and then as you watched it go by, what you would have is the contracted length. And this is the length. This is the length length while object is moving relative to you. moving relative to the observer. So when I say observer, when I say moving relative, you always mean the observer. So it's when it's moving relative to you. Observer, ERS, sorry, in the observer's frame. So that's proper length and contracted length. This is what it is if it's not moving relative to you. This is its length if it is moving relative to the observer. Oh, and another way you can write this, sorry, delta x is just L prime, it's just the length of it, and gamma L. So I don't care. I don't know which way you're going to see it more often, but they mean the same thing. Sorry about that. So that's the contracted length and the proper length. And so I had to do a problem on this when I was in college, and there were some interstellar particle. I don't remember what it was. My professor was a particle physicist, and he said there are these interstellar particles, and he told us some speed, really, really close to the speed of light, like 0.999% the speed of light. And he said, or not 0.99, 99.99% the speed of light. And he said, how wide would the universe, or not the universe, our galaxy, which is 100,000 light years across, how wide would it appear to be for this particle if you were moving along with it? And the answer was something like it was only like 5 miles wide instead of 100,000 light years. So this can be a very big effect if you're if you're moving really fast near the speed of light. Otherwise, if you're moving slow, that gamma goes down to being basically 1, and it's not a big deal. So now that we've talked about time dilation and length contraction, I want to mention something called muon decay. So there's a lot of things that have been done to kind of show that this stuff actually happens, and it's not just funky math. There have been experiments done with really, really accurate atomic clocks where they leave one down low and they put the other up high on a mountain, where they're going at different speeds, and they see that they're going, or I say they leave one down on the ground and they put another one like in an airplane and they fly it all around for a while, and then when they bring it back to the one that they left on the ground, they find that the one that flew around in the airplane is behind the one they left on the ground. Not by a whole lot of seconds. I mean, if you flew around in an airplane for the rest of your life, you may gain like 1 or 2 seconds onto your entire life that would be dilated. And of course, your time would dilate, so you wouldn't notice it anyway. So it's not a very big effect at our human speeds, but we can measure it with atomic clocks and see that there really is this. Of course, GPS confirms this kind of stuff, the time dilations and things like this, these Lorentz transformation artifacts. It shows them by every time it finds your position properly, because GPS is just a big clock system, and the satellites have to adjust for their speed relative to Earth and time dilation occurring. But there's also something that's a little more straightforward, is this muon decay. So there are these muons that decay in a fraction of a second, and they're created up in the upper atmosphere. So let's say that's the top of the atmosphere. They're created up here. And classically speaking, at the speed they're traveling, they shouldn't make it, or at least not many of them should make it down to the surface. So this is our upper atmosphere, and this is the surface of Earth. They shouldn't make it because the time that it would take them at their speed to reach the surface of Earth is too long, and they would decay in that amount of time. But it turns out, if you go outside and you have a little detector, you can actually detect something at something like 70 or 80% of the ones that are created in the atmosphere are still around by the time they reach the surface. So, classically speaking, this doesn't make any sense. But if we take into account this time dilation and this length contraction, well, for us, looking at it, we can say that, well, their time dilates. So even though from our perspective it takes them many times the amount of time, the length of time of their half-life to reach the surface, from their perspective of how fast they're going, it is actually less than a half-life for them, and so from our perspective we say, all right, they make it. For their perspective, if you want to think it from their perspective, they think, all right, I'm not moving, but when they look at the atmosphere, this length of the atmosphere is contracted, and so yes, to their own perspective, their half-life is exactly the same, but the distance they're traveling through the atmosphere is a lot smaller than what it would be. So from our perspective, it's time dilation that allows them to make it. From their perspective, length contraction allows them to make it to the surface. Now, in your book, there's a nice little thing where they actually work this out and show you the math behind it, so I'm not going to redo that for you, so feel free to go take a look at it. And look at any other examples you can find. You can Google up some of this kind of stuff. And there's a lot of evidence. I would say that this stuff is probably the most well-tested of any of the scientific theories that I at least know of. And every time you use GPS, it is a nice, good confirmation of this. So, feel free to take a look at that stuff and do some practice problems on this and get yourself comfortable with it. And yeah, that's it for this one.